Today we're here at PCIM 2026 and it has been a fantastic event and we've seen all kinds of new technologies coming out. We've seen O1's been revived and today we're here at Texas Instruments joined by my very good friend Harold. Thank you for having us here today.
Thank you for taking the time.
Now before we jump into all of this cool and awesome stuff you've got going on here, just tell the audience who you are, what you do and what you like to do in your free time.
Okay, my name is Harold Parsuba. I'm a systems manager at energy infrastructure at Texas Instruments. I'm located based out of Freising, Germany, and we are doing reference designs or demo designs that show basically how well these products that we have at TI, these 100,000 plus devices, can be used in an application. And the things I'm working on is energy infrastructure, and energy infrastructure ranges from how you get the power, how you generate it, how you distribute it, and how you use it downstream, maybe in a data center or in a motor drive or whatever.
Fantastic. And last question, what do you do in your free time?
In my free time, I love to spend time with my wife. The kids are out of the house.
I've got that one to look forward to, not in 18 years' time.
Making long distance walks with my dog.
Fantastic, and I think that was the right answer. And your wife is intensely watching this video, so you make sure you mention me.
I hope I made it in the wrong, not in the wrong direction. Right? So first wife, then the dog.
Perfect.
If I ask her, might be different.
Now, a quick question before we dive into the hardware, and I have to ask forgiveness because I didn't realize that TI also produces GaN devices. I thought it was just the gate drivers.
No, actually we are working on GaN devices since 15 years.
Blimey! I've been out.
15 years,
yeah.
Yes, and we are already in the third generation of GaN devices. We are focusing on 650 volt GaN devices. We started with that. This is the sweet spot. We have also a portfolio that goes down to 100 volt, and we are expanding to a 200 volt technology and also to a 20 volt technology later on. So GaN we see in all size constraint applications, power ranges below 20 kilowatt, 30 kilowatt. We see a good fit for GaN devices. So that technology we developed since 15 years. What makes us a little different to some of the other manufacturers of power semiconductors, we try to integrate, or not we try, we integrate the driving circuits, the gate drivers, into these GaN modules. Makes it easy for the developers to build a system. And last but not least, if you integrate the gate driver into a GaN module, EMI radiations become much better because you don't have a discrete gate driver that goes a few millimeters, sometimes
right
centimeters over the PCB and radiating like crazy. So that's the philosophy. Every GaN device that we have will have at some point in time a gate driver integrated, plus maybe some power management, plus temperature sensors, plus overcurrent detection. So we want to make it easy that the device itself protects in a faulty condition.
A quick question, you mentioned about a sweet spot for GaN device being 600 volts.
650, yes.
650. Can you explain why that's a sweet spot?
This depends on the on the way you build these devices. These are lateral devices, so they are built on silicon oxide.
Are they plain like
yes.
that? Yeah.
And with a certain amount of size you have, you can realize a certain low impedance.
Right.
This is different than SiC. SiC is vertical technology where you go through the complete die. It's simply the cost and size is basically
it's like an optimal point.
Yeah.
Is it kind of?
Yes.
So it's kind of like it's like if you go bigger, it might go more efficient or whatever.
Yeah.
But then you get other issues. So it's kind of like this nice little valley where it's just right.
Exactly. So with 650 volts applied, you can make reasonable, cost-attractive devices.
That's very
and
interesting.
Of course, there are attempts to go to higher voltages. So GaN is moving into 900 volt, eventually 1200 volt. If there is more, then maybe it goes vertical. As of today, lateral 650.
Or maybe when you go too high, that's when SiC comes into the play.
Absolutely, and this is where we clearly see that SiC has a benefit over GaN today. You can see at the show that some of the vendors are showing SiC modules that are 2.3 kilovolt rated, 3.3 kilovolt rated, which make them attractive for some high power, high voltage applications.
Now, you mentioned about reference designs and modules, and one trend which I've actually seen sort of coming into play is you can buy individual GaN switches, you can buy the gate drivers, but then we're seeing more modules, like you say, where you put them together. Do you think in the future that because driving GaN and SiC devices is quite complicated and difficult, that engineers are just going to go for a whole complete module solution anyway and not really try to build these things themselves?
It depends on the power level you look at. So we have started to integrate 400 watt, 500 watt power module, 3 phases already. And we have a demo over there. That makes sense to put this into one device. You can cope with the power dissipation. You're always in the range between 1%, maybe 2% of power dissipation. So if you do the calculation, you have a kilowatt, and 1% is already 100 watt.
Yeah.
Which means if you have 2% losses in your system, you need to get the 200 watt out of the device,
There's
right?
a lot of heat
Which is
very
a
quickly.
problem.
Yeah.
So it's better to distribute this over PCB and have a cooling system behind it. And this is why for high power applications, you basically go into different locations on the board and distribute the thermal performance a little bit around it.
And what would you say has been the biggest challenge so far for engineers when it comes to GaN?
There's multiple challenges. So people are thermal cooling. You have a certain amount of power in a small package. You can cope with that if you have topside cooled devices. You put thermal interface material in and have a heatsink that has maybe liquid cooling or forced air cooling. The second problem with GaN allows to go much faster with the switching frequencies. That in turn means these passive components, inductors, capacitors, they can become smaller. Which means the magnetic material has different behaviors at higher frequencies. It's a trade-off where to draw the line.
Yeah.
Where is magnetics already losing the capabilities being magnetic from a frequency perspective, and where do I still operate at a decent low switching efficiency?
Is it harder to get like higher Q inductors as you go faster in frequency?
Yes, absolutely. Yes, the magnetic material starts to saturate earlier, and you sometimes need to change to different magnetic material. And we are not developing the magnetic materials.
Oh no,
we have expert partners we are working on,
Yeah.
but we give them basically the frequencies we
Yeah.
try to operate in, and give you the saturations, currents, and then they start building that. And the whole industry is moving towards this supporting GaN with these high switching frequencies. And when you do the calculation, and you look at a power converter that was operating in the past with a few kilohertz, IGBT based, yes, IGBTs are darn cheap. But if you look at the total system solution, you have a boost inductor there that is
Massive,
the size of a stroller, right?
And the weight as well.
The weight is important, the size is important, and it costs. It's
Yeah.
a lot of copper, it's a lot of metal.
Yeah,
And that reducing the overall cost by going with switching frequency higher, you save a lot of money.
And one trend I've seen is a shift away from sort of round core copper wires and inductors to like the flat cores. So
Yes,
it's quite
the flat
interesting.
cores. We see that. We have actually one example here where we use flat cores.
So these are flat ones. Oh yes,
These
you're right.
are
Yes,
flat
yes.
cores. These are
Yes.
flat cores, and this is actually a GaN-based 30 kilowatt 3-phase converter. So it operates from 3 phases up to 480 volts, and you can do a current up to 36 amp per phase. And that gets us to the 30 kilowatts. And we use, for this one, we use flat wires, and it's operating at 65 kilohertz. So compared to this
that's fast.
That's fast, and it's in a flying cap topology.
And the size of it as well for what it's doing.
It's with using a flying cap, 3-level flying cap topology, the frequency doubles basically at the output, which means this inductor can be used to filter off double of the frequency. Makes the size smaller. It's a very cost optimized and high power density design.
But it's also interesting to see that as we get to these higher frequencies, these new technologies, the complexity of the design does increase. So
It is, from a functional perspective, it is the same. The complexity is easier because we don't need to design any gate drivers. It's the complexity in sense of you spend more time on the magnetic components and the passive components. Yes, the design work to build this basically and simulate this in PCIM and other simulations.
And I think when I talk about complexity is like if you try and do it yourself with the individual gate drivers, with the individual chips, doing the research to figure out how the ringing or the EMI works, which is where your modular solutions come in.
They help and will make the life much, much easier.
So could
by
you
the
sort
way,
of-
these are these modules what we have here on this picture. on this demo. So these are these GaN devices that we are using. So we have 4 per phase. It's flying caps, so you need 4 switches. They are topside cooled GaN devices, 10 milliohm, 650 volt rated. The DC link on that design is going up to 900 volt.
900 volts.
900 volts. So we
Blimey.
operated each one 500.
That's quite interesting because I always thought that like GaN was more low voltage and then your SiC is high voltage. So when you go to a certain point, you just go SiC. But you're saying that eventually you're going to go higher and then stay in the GaN field.
So you can work with lower rated power devices if you stack them on top of each other. That means you go from a 2-level topology to a multi-level topology. In this case, it's 3-level. It could be also done in 4 levels, 5 levels, and then with every 2 levels you increase, you're doubling the voltage.
And so
3-level flying cap is a well-known topology now, and it's pretty cost efficient to work with lower cost, lower voltage devices to build up systems that are typically addressed with high voltage.
So when it comes to the, you mentioned about combining the switch with the gate driver. Is that in the package or is that as a module like this?
It's in the package.
The package itself?
It's in the package itself.
So that's got the gate driver and the chip?
It has everything inside. So it has all the protection features in there. You drive this not with a gate drive signal that goes minus and plus, odd values, plus 14 volt and minus 4 like in SiC. You apply only a digital signal that is 5 volt levels.
Oh, 5 volt. Oh, I love that.
Makes it easy also from
absolutely
connecting it to a microcontroller.
No, that's exactly the point, isn't it? Because then you can make those things smart and intelligent.
Yes.
You don't have to have the protection circuits. You haven't got 500 components trying to filter the signal.
Exactly.
Oh, I need a negative voltage generator so I can drive it going down.
And I need a few diodes to do DSAT detection.
A Zener to protect it as well. And
all done inside.
That's amazing. That's absolutely
you
amazing.
Make engineers' life easy.
Oh, I know, and because there's nothing worse. Do you know? I tell you what it reminds me of. This is going a long way back. But do you remember like the very old early microprocessors, like the 8088 or something, where they would have -5 + 5, -12 + 12 voltage signals, 2 clock phases, and it's just like, come on. And then the Z80 came out, and it was 1 5-volt rail, 1 clock signal, and this is like the Z80 of that. I think.
Moving in that direction.
It is.
It's moving in that direction.
And I'm guessing then, like, so when it comes to actually designing and implementing these things, how does Texas Instruments help customers with that?
So one thing. First of all, we have a lot of collateral on TI.com where we show per product how to use it in an application use case. If this is not sufficient, we do these reference designs where we show, okay, these products you can use in a particular configuration in that particular end equipment. So we are doing reference designs for power converters that can be used in solar, that can be used in OBC. So we do complete subsystems, which we are not selling. We just demonstrate how you can use the TI parts in these.
And then you give out the schematics, any source code. But it's interesting because you spend all of this effort to design these reference designs. Do you think there might be a point where Texas Instruments goes, well, customers just want to buy that, so why not just give them this? Because if you guys are the experts in your own chips and you know how to make them properly, so maybe, do you think there'll be a point where someone goes, well, look, I just want to buy that because I want to stick it in an EV or something?
It happens from time to time that a customer says, can we buy that? We want to commercialize it.
Yeah.
From a reference design to a commercial product, there is still a long way. There are certifications. There are things you need to build in your own recipe for what are you differentiating with your product in the market you're trying to address. So this is truly a starting point. But what we have seen is that customers have been taking core pieces from the layout databases we provide in Altium and other formats. They take this as a base, copy that over where the critical design components are, and build the rest around what they do for productization by themselves. So they are a good starting point, by no means a commercial product, and TI has no interest to sell those.
Because all I'm going to say is I'm looking at these reference designs, and every time I've seen a TI reference design or a test board, I have to admit, the PCBs are absolutely they're so gorgeously laid out, honestly. I'm not, this one here in particular, perfectly organized, rows, cutouts, it's just honestly fantastic. So with all of these reference designs, these new technologies coming out, what would you say is the singular most exciting industry for you that you want to see this getting into?
Certainly we see a strong push towards data centers.
Data centers.
Data centers, they changed their architectures quite significant.
Yeah.
GaN fits perfectly there because it's a size-constrained application, it's high power. I clearly see GaN technology there. And also with the integration of all the gate drivers, it simplifies the board design, makes it small.
And I was also going to say as well, I'm guessing these are very good in terms of EMI as well, where noise might get injected into buses and stuff. So that's going to be useful for a data center.
This makes or breaks it, right? The other area where I see clearly in the complete power distribution, the historic ways it has been working was you take a mid-voltage grid, you have a low-frequency transformer, then you have a AC-DC that is generating an 800 volt DC or 400 volt DC that is being used for other purposes. So what we see right now is these low-frequency transformers, they operate in a certain range, they have some limitations. A technology that would fill that gap is solid-state transformer. Solid-state transformers are basically an implementation where you can cope on the mid-voltage side with 10 kilovolt up to 34 kilovolt by stacking pieces, multiple pieces of 1 kilovolt, 2 kilovolt AC in series, have a high frequency transformer and generate a DC at the output. This is where I see these technologies going as well. So that's also a big field where I feel this could be very, very important.
So with the last question now, and this has been an absolutely fantastic demonstration of the reference designs you guys build, but for engineers who are watching this video, if they want to get involved with these reference designs, the solutions that TI provides, what would you recommend that they do?
It's pretty simple. Go on ti.com, search for TI designs. You can type in a title for what you're looking. You can type in a title, three-level flying cap, or if you know the number TIDA, go check out the material we have. We have full design reports. We have full databases on Altium, schematic, everything incorporated as a starting point. And if you don't find anything, you can always write to your contact at TI, and we will get an answer to you.
Fantastic. And all I can say is it's always a pleasure coming down to the TI booth. Thank you ever so much.
Thank you so
for having
much.
us here
It was my
today.
pleasure.
Thank you very much. Thank you.